Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our modern C++ series. In today's lesson, we're going to be taking a look at one of the most important search algorithms there is. If you haven't guessed it already, it is binary search. And just to prove a point here, let's go ahead to the web and search most important algorithms. And pretty much any list that you look at here, I'm going to go ahead and just click on this website here because I'm aware of it, shows up binary search. So I'll give you a brief introduction to binary search in a moment here, but just know it's a really important algorithm in computer science. Why is it really important enough to include in our algorithm standard library? Well, it's for supporting fast searching operations. And oftentimes when we've been talking about the standard library and logarithmic complexity, well, binary search is usually behind the scenes. But why have it as a building block in the algorithms library? So I'll go ahead and answer that as we go ahead and look through binary search. But let's go ahead and continue into CPP reference here into the algorithms library. I'm going to go ahead and scroll down here past many of these different standard library functions that we've looked at, modifying, non-modifying sequence operations, and we'll get all the way down past partitioning operations, sorting operations, which we looked at, finally to binary search operations. Now it's important in parentheses that you see that these are supported for sorted ranges. If I try to run a binary search on something that isn't sorted, we may or may not get the correct result. It's sort of not the deterministic thing that we want. So I'll try to show an example of that. But again, the important point being that we need to sort our containers that we run binary search on. So with that said, anyways, let's go ahead and dive into binary search, which helps us determine if an element exists in a partially ordered range or the full range itself. Okay, so with that said, let's look at binary search here. And we see that we've got a const expr version here since C++20, so we'll go ahead and work with that. But the basic idea is we need to figure out what range are we going to search from, meaning the start, the end, and what value are we going to be looking for. So I'll go ahead and highlight this version here. And we can actually modify the comparator here if we want. So you could use, if you're using integers, for instance, stood less or stood greater than, to change how the binary search works. But let's just go ahead and do a quick refresher on binary search, and it'll help us think about this a little bit. But the basic idea is if I have some ordered collection here, and let's go ahead and write out an ordered collection here, 1, 3, 5, 7, 9, something of that nature here. And again, we can see the ordering in ascending order. The numbers are growing greater with each successive number that's added. The basic idea is if I am searching here, I start in the middle. And then I'm able to, well, if I'm searching for, say, the value 1, eliminate everything to the right here. That is greater than, well, our current index. So if it's not the current index, then we know that we must look to the left here. And then our binary search sort of proceeds here with 1 and 3. So I'll look halfway through the collection here between 0 and 1. The first index here, it's not 3. So then we'll look at our next index here, the remaining part of this structure, and we'll find that we have 1. So that's the basic idea. And it's saving us from having to do a linear scan of each element here. So again, as our collections, whether it's a vector or an array like data structure like this, grow very large with the number of inputs that we have, well, binary search is effectively cutting half the work that we have to do each step along the algorithm. So there's many videos on binary search. I'm happy to do a more formal analysis on it, but that should hopefully give you an idea of what's useful here. Now, in the C++ scheme of things, what's interesting here is that we have a first and last iterator that we're going to be passing in here. So it sort of begs the question, why do we need this binary search function here as a building block? Well, let's go ahead and look at CPP reference again here, and let's look at some of our containers. For instance, let's go ahead and look at something like a map here. Now, as we discussed, map is a sort of associative container here where we can search for things. And behind the scenes, there is some sort of red-black tree. Now, again, we've covered in the map video, so you can check out the playlist below on the actual performance here. But let's go ahead and see if I have some operation here, like find, for instance, that in fact it is logarithmic. So why would I want to binary search over this data structure when it's already effectively built in? There's specialized member functions for this. So why do I need this general purpose building block? Well, again, with the design of the standard template library, what I find useful is that we can do partial ranges, and we could still do that with the find, right? Because it supplies a beginning and ending iterator. But again, it's just more fundamentally indicating exactly how we want to do that search, again, versus maybe a linear scan or some other type of algorithm. Now, the other interesting thing about binary search is it returns us a true and a false value. Because again, we're just searching if we find something or not. Whereas a lot of those find functions would return us the actual iterator. And that actually might be useful for us as, well, we'll search through the algorithms library here, and I'll get prepared for us some of the other binary search operations like lower bound and upper bound, which do return iterators for us. Okay, so maybe that's enough here, and maybe we're getting in the weeds here. But again, these are the generic building blocks that we have available. So anyways, let's just look at binary search and see that it's available here. And we're able to search between a range, and whatever that range is, it just needs to be partially ordered. So again, between our starting position and wherever our ending position is, whether that's the whole container or just a subset of it. All right, and we'll do the comparison based off of, by default, a less than comparison. And again, we could do these with custom objects if we need, but that's what's needed. And again, we need some sorting to be done here. Okay. All right. So let's go ahead and scroll down. We'll go ahead and see some different implementations of binary search. And we'll actually see that lower bound, which is part of this subset of the algorithms library, is in fact a way to implement the binary search. But again, lower bound is just returning us the iterator. That's the difference. And upper bound also returning us the iterator. Okay. So let's look at an example here where we can perform some searches on the container here. And we'll actually go ahead and write something out here. Now I'm going to go ahead and put these not in order just so we can see, what some results might be here. So let's see, like 19, 21, 57, 45, the value 4, something like that here. Just give ourselves a number of different numbers to work with here. It doesn't matter if we have an odd number or even number, binary search will still work. Again, it might be another reason to use something like binary search so you don't have to worry about those corner cases in your own implementation. Okay, so now what I want to go ahead and do is make sure that we sort V here from the beginning to the end. And then let's go ahead and set up our binary search. And I'm going to go ahead and there's a nice thing in IO manip here. I want to return true or false if we find something. So I'm going to go ahead and set up the cout stream to write out true or false values when we find a value in our binary search. Okay, so let's do binary search. Let's look through the whole range from the beginning to the end and the value that we want to look for. Let's go ahead and search for 5, for instance, and we'll just use auto here and determine if something was found. Okay, so let's go ahead and see if this does the trick here. Say if what the value of found is, and we'll go ahead and just print that out and see if our binary search works here. Okay, so go ahead and compile with C++20. Don't necessarily need to, but we get that const expr version otherwise. And whoops, one little mistake here. This should be, I believe, bool alpha. And then we can go ahead and give this a run. And one set of missing parentheses here. All right, there we go. And we get found true. Okay, so of course we found the value 5. We can see that it is here. Now when we sort this out, of course, this is going to put it in order here and basically run through this same process that we had of, well, first sorting our collection and then effectively getting rid of half of the entries and even looking to the left if all the entries are less than our current position, like we did in this example, or to the right if the value that we're looking for is greater than the current value here. Now, of course, we will land and test the current value in the implementation of binary search to see if that's what we're actually searching for. So that's the idea here. Now, if we don't sort this and we run binary search, let's see what happens here. It does happen to return us false. That's maybe a false positive here. So we don't know if that's true. Maybe if we add enough numbers here, we might be able to get it to return true here. Like, let's see if I just put in the value 1 or something here. It might work here. But again, it's not sorted. So again, you want to make sure that your collection's sorted here. So this is where, again, it might be worth going through the effort of, let's put a few of those numbers back in here. Using some of the different functions that we've learned before, like if, and let's just go ahead and do is sorted from v, the beginning, for vector to the end. And we want to do this explicitly if it's not sorted. Then sort it, and then make sure that we find our value here. Whoops, and let's just add it in one more parenthesis. There we go. And there we go. So that's a pretty efficient way to do the binary search. In some cases, making sure that we check if something is sorted first. Now, with that in mind with binary search, that's, again, useful for just, again, telling us if we have an element in our collection. But if we want to actually do something with it, what do we actually need? And that's where, again, having some of these other standard library functions like find could be useful. So we actually have a few more here, as I've prepared, like lower bound, and let's go ahead and get the other one here, upper bound, which I do have. And what lower bound does is it returns an iterator pointing to the first element in our range where we're doing the binary search. So it's effectively very similar, except that it's actually returning the iterator to the element, okay? So let's go ahead and we can see some implementations. If we actually look at the implementation of this, we can see in some contiguous data structure that has a forward iterator that we're basically just, and again, this has to be a sorted range, doing the binary search here. Okay, so this is one way that we could implement it here. Okay, so let's go ahead and test it out here and see what the difference is with lower bound. So let's just do auto lower equals standard lower bound. And again, the signature is going to look very, very similar here to our binary search. Let's just get it in the view here. That we have our iterator from the starting position, the ending position, and then the value that we're looking for. Again, we can change the comparator if we want to change how this works. Okay, but that's the basic idea here. So we're basically just going to copy what we have above, this time without any typos, hopefully, and see here what lower is. And let me just try to write out lower here. Let's see if it'll do the trick there. And this is going to, because this is an iterator here, and let's see if we can see what the actual message is. Yeah, it's telling us that this is some normal iterator here, etc., etc. So couldn't figure out a substitution. Again, just remember that this is an iterator, so we need to dereference it, and then we'll actually get the value back, which is, in fact, 5, which we are searching for. Now, again, this lower bound could be useful because, well, what happens in the instance that we have, well, a bunch of elements that happen to be equal? Now, in the case of integers here, we might just be searching for, 1 to see if it is in this collection here. Okay, so you're sort of treating this as some sort of query. Is this value in my vector? And you do a binary search on this sorted collection. That's fine. But what if you're actually doing something like processing these, right? You want to actually find all of the 5s here. So you can find the lower bound, which is an iterator to that 5, and then kind of keep walking forward while there are still 5s or something. Okay, so you'll have that actual position and can do something with it. So likewise, if we go ahead and run this with upper bound, okay, and we'll do sort of the similar test here. What upper bound does is it doesn't give you the first element that's less than or equal to what is found, but it gives you the first element that is greater. Okay, so let's go ahead and look at upper here. We might want to actually list out these numbers just so you can see here, but we get a 7 here. And if I go ahead and look at my collection here, and actually, instead of looking at it, let's just print it out here, just so we can see the actual numbers here. Because again, we're programmers, we can do these kind of things. Let's print out a vector. I was using class template argument deduction here, but let's just be explicit. Let's assume these are all ints here. Let's pass this as const and by reference, so we avoid copies with v here. And then let's just go ahead and I'll use a for each loop range-based loop here to write these out here. Okay, so for all of our elements, these are integers, so I'm not going to worry about being extra efficient here, but then let's just write these out. The element and maybe a space between them. And at the end, a end line. Okay, and you've seen me do this if you've been following along and subscribed to this series enough times. So let's go ahead and see the sorted collection here, actually. Let's do it after here. Print v and pass in v. Let's see if we did that without any mistakes. Whew, okay, there it is. So basically I just want to copy and paste this, or we could just look at it and see that the upper bound is 7 here, right? This is the first value that's not satisfying this here. Now our iterator here, and it's probably worth actually printing out these memory addresses. So let's actually go ahead and do that just so we can see these different elements and see that lower is, again, returning us the least of these here. Because again, remember what a binary search is going to do is effectively, start from the middle and say, okay, you're looking for 5, so get rid of everything that's on the right side and start searching from here. And then it's going to search from the middle of whatever is left, but we might have lots of 5s here. So again, let's see which one's returned here. And the way that we're going to do this is let's print out the element and let's just print out its address. Okay, and let's go ahead and format this just a little bit here. Again, this is an experiment to fully understand what is going on here. Actually, let's do, element and then address. We'll do a little tab there. That should do the trick here. And let's do these one line at a time here. Otherwise, it's going to get a little bit messy. Okay, so let's start with that. Make sure we got everything. Okay, so we've got the address of all of these here. And oops, looks like, oh, I see. Actually, this is just going to print off the address of that element there. So I'm going to have to rewrite this. Yeah, let's go ahead and rewrite this here. Let's just use a regular loop here because I want the actual addresses here. Let's see, the index. Okay, let's do this totally properly. The index from 0, because I want to actually print off the actual address of each of these values on the heap here. And we're passing this in by reference, so we should be getting those actual values. So let's go ahead and see if that is true. So while idx is less than v.size, idx plus plus. idx is just a common abbreviation for index. Then we'll paste that in here. And instead, we're going to look at v, the index, and the address of v at the index. All right, let's see there. We should at least get some different values that are incrementing. And you notice that in the previous example, let's see if we scroll up, you can actually see the address space change here, which is probably telling you something about, like, is this a stack allocated thing, or, where does my heap start, which is kind of interesting. Again, if you're happy with, at this point in the video, binary search in lower bound and upper bound and understand that, that's fine. This is just going, another step further to show exactly what's going on here. And let's go ahead and print off when we found the lower and the upper addresses here. Okay, and let's see where they match. Okay, and well, remember, this is kind of running the same problem here, right? This is the actual address of this sort of placeholder that's on the stack here. So how do we get the address of the thing that we want? Well, we dereference it and then take the address of the actual element. And let's see what we've got here. So the question is, for my lower bound, is it the first 5 here? So we just have to compare the address here. 0556C. Okay, these are all 0556C. 4 2s. I see 4 2s. And I see B27C. B27C. All right. So there it is. So you can kind of understand how lower bound is working there. And then again, what I would do with this is what I would say is, again, just to make use of lower bound, let's go ahead and, well, let me just maybe explain it because we're getting long enough here. I would just look at the next element and then you could just do a linear scan from there and test, is it 5, right? You don't want to necessarily keep running, a binary search or something, like removing this and then binary search, because once you've already found your collection, if your goal is to just grab all the fives and then do something with it, our CPUs are very good at looking at elements that are next to each other. Okay, that's a little bit of another talk here, but those linear scans aren't necessarily always that expensive, if you have small collections or looking at elements that are next to each other because of cache locality. Alrighty, folks, so with that said, consider binary search as another generic way or a building block to search for elements, and lower bound and upper bound as helpful ways to either, implement your own binary search, or if you want to find successive elements in a binary search. And the use cases for these building blocks could also be kind of niche in some ways, meaning that you might also use upper bound or lower bound as a quick way to write in one element into this collection and do an insertion. And if you're not doing that frequently, that might be a pattern that you could use. Again, we've talked about how inserting inside of a vector could be very expensive, but if this data structure is mostly not going to be modified or written to, and you're going to do more reads than writes, that might be something that you, again, consider these as building blocks for. Again, use the STL because it is implementing these things correctly. It's giving you the right behavior, again, for finding the least element here, as we explored here by looking at the memory addresses. And there you go. There's binary search and lower bound and upper bound, which are useful tools along with it. Alrighty, folks. So with that said, as always, you can track your progress on these lessons on courses.msha.io here. So feel free to sign up. It's free. You can track your, again, progress in a non-distraction, or I should say with less distraction environment, and check out some other great courses as well. So with that said, folks, let me know if you've used these building blocks for anything interesting, any algorithms where maybe you've seen them come up, which might be fun to implement or for us to even do a more formal analysis. And as always, folks, thank you for your time and attention. I'll look forward to seeing you in the next one.